All right, applied calculators. I figured I would present a few more examples for those people who just want to see the process of U substitution done a little bit more, just to get a little bit more comfortable with this. So let's try something that isn't terrible, just to make sure we're in the groove. 4x cubed times x to the fourth plus 3 to the third dx. We could expand the brackets, get a really long polynomial, do the power rule one term at a time, and get the antiderivative that way. But we also recognize that the derivative of this piece is hanging out right there. And if the derivative of this piece is hanging out right there, then u should be x to the fourth plus 3. I don't want to be x to the fourth plus 3. It doesn't matter. Then du dx is 4x cubed, which means with a little bit of chicanery that we know what du is. And that means that this integral, well, the 4x cubed dx is du, and the x to the fourth plus 3 cubed is u cubed. How do we take that indefinite integral? Well, that indefinite integral, raise the power by 1, divide by that power, plus a constant. And then we don't write u, we write u. But what's u? This is u. And sure enough, we have a way to find antiderivatives just like so. Let's try the integral of x squared times radical x cubed plus 1. Well, if you've been following the bouncing ball in the text and in the videos, then you know that things in brackets make for good U's. And sure enough, the thing in brackets has its derivative sort of hanging out over there. And so we want to say that U is x cubed plus 1. And that means that the derivative of U is 3x squared, which means that du is 3x squared dx. But that's not what we need. We need x squared dx. So if we need x squared dx, that means we need something 1/3 as big, 1/3 as big. And that 1/3 can come outside of the integral sign. It can come outside. It's a constant multiple, so that's fine. And then what's in parentheses? Well, it's the square root of u. Well, how are we going to do this? Well, the square root of u, oh, I should use a different color for that. The square root of u is u to the 1/2. So how do we take the antiderivative of u to the 1/2? Well, the power rule says we add 1 to that power and then divide by that new power. How do we divide by 2/3? I'm sorry, how do we divide by 3/2? We multiply by 2/3. To divide by 3/2 is to multiply by 2/3. And so what do we have? Well, these fractions multiply to 2/9. We're not going to write u, we're going to write u plus a constant. Every time, things in parentheses make good u's, things in brackets make good u's. Things in denominators make good u's. But what if you've got them both? What if you've got something in brackets in a denominator? What happens with that? So the question is, is u the square root of x squared plus 9, because it's in the denominator, or is u the thing in the square root? Take a moment and think about it. Well, the derivative of this is basically hanging out up here. The derivative of this is much more complicated. So u is x squared plus 9, which means du dx is 2x, which means du is 2x dx, which means the thing that we want is half as big as that. Well, what does that mean over here? That 1/2 comes outside, x dx is du, and we've got 1 over the square root of u. Well, how are we going to do that? We don't have a rule that deals with that unless we look at 1 over as a negative exponent. And if it's a negative exponent, then we can deal with it because we have a power rule. And the power rule says that when we have u to a power, we add 1 to the power and then divide by that new power. How do you divide by 1/2? You multiply by 2. Those go away like you will soon. You get u to the 1/2 plus a constant, but we don't write u, we write u. All of these questions go the same way. There's a part of the question whose derivative is hiding in another part of the question. And we use that to rewrite the problem with a complete change of variable. We use the letter u because we can't use x effectively. Okay, I hope that this is helpful extra. We'll see you in class.